Hey guys, today we're looking at section 5.1, which is going to talk about extreme values. So let's start with the definition. Extrema are maximum and minimum points on a given graph. So there are several types of extrema that can occur on a given graph. So let's look at a couple of these. So if you have an absolute or a global maximum, that is the greatest y value on the entire graph. So your absolute slash global maximum is the greatest y value on the entire graph. And similarly, your absolute slash global minimum is the lowest y value on the entire graph. So absolute means the highest and the lowest on the entire graph. A relative slash local, maximum is the greatest y value on a given interval. So that's the greatest y value on a given interval. And similarly, the relative slash local minimum is the lowest y value on a given interval. And then the last one is a critical point. So a critical point is the point where the graph's slope changes signs. Wow, I'm having a hard time talking today. So this is where the graph's slope changes signs. So more specifically, we're talking about where we have a slope of 0 or an undefined slope. So I'm going to do that just below it right here. The slope is 0 or undefined. And let's see if we can fit both of those in the box right there. There we go. So it's where the graph's slope changes signs, so where the slope is 0 or undefined. So let's look at putting some labels on this graph that we have over here. So for an absolute maximum, I would say the absolute highest point is this point right here. So I'm going to say that this is A, an absolute maximum. Then we have absolute minimums. And on this graph, we actually don't have any because of these arrows right here. So when you have arrows like that, there is no absolute minimum value because it's going to keep on going down forever. So we actually don't have any absolute or global minimums. The next one is a relative or local maximum. So on a given interval, that would be a relative. So I could say that this point right here is also a relative or local maximum. This point right here could be a relative or local maximum, and this point as well, because you could take a given interval that's just a little section of the graph, and that could be a relative maximum. So if we have relative or local minimums, we have a couple of those. We could have a relative or local minimum here, or at this point right here. And then a critical point is any point where the slope is 0 or undefined. So a critical point is all of these points that we just talked about. It's a critical point here because my slope is 0. My slope is 0 here, here as well. The slope is 0 here, and here it's a sharp turn, so the slope is actually undefined. So it's still a critical point, it's just an undefined slope instead of a 0 slope. So let's look at some more examples. So it says label the extrema and critical points on each of these graphs. So I'm going to use those same letters that I was using from this table right here, the A, B, C, D, and E, just because it's a little bit easier to write letters instead of having to write all of these words. So if I'm looking at my parabola right here, these arrows mean that it's going to go up to infinity. So that means that I'm going to have no relative maximum or absolute maximum. But right here, I have an absolute minimum, so I'm going to say it's a B for absolute minimum. You also could call it a relative or local minimum, so I'm also going to put a D. And it's also a critical point because we have a slope of 0 right there. All right, for this one right here, This arrow once again means that I'm going to have no absolute or relative max. And I once again have a point down here that is an absolute minimum, so I'm going to put a B. So that means it's also a relative minimum on any given interval that includes that point, and it's a critical point, so I'm going to put an E right here. This point right here is an endpoint, so we don't really talk about the endpoints when we're talking about our extrema. So we look at the arrows, and then we look at the points inside the interval, but not necessarily the endpoints. So same thing here. I'm not going to look at this endpoint, or really this endpoint, but because this one is an open point, there is no max. Because it's going to get closer and closer and closer to that value of 5, but never actually reach it. But we do, once again, have a minimum right here, and it is an absolute minimum, a relative minimum, and a critical value. So it's that same BDE that we were talking about. Okay, let's look at some different shaped graphs. So if I'm looking at this one right here, this arrow means it's going to keep on going down, so I'm not going to have any minimums. And we've got an open point here on this end, so we're not going to have any maximums either. But this point right here in the middle, I'm going to say is a critical point because my slope at that point is undefined. So that is our critical point there. And then I'm going to look at this point right here. And remember, we don't talk about our endpoints, but right here, this would be our absolute maximum. So I'm going to say that this one is A for absolute maximum, which means it's also a relative or local maximum. So I'm going to say it's a C. And that means it's also a critical point. So I'm going to put an E. And then this point right here, it's not our absolute minimum because we do have this part of the graph that keeps going down, but it is a relative minimum. So since it's a relative or a local minimum, I'm going to put D. And it's a sharp turn, so our slope there is undefined, which means it's a critical point, so it is E. And looking at our last one right here, remember we don't look at our endpoints. So in between, I don't really have any local mins or maxes, and I don't really have an absolute min or a max either. But I do have this critical point right here because I have a slope of 0 at that point right there. So even though it's not a minimum or a maximum, it still is a critical point. All right, let's look at another graph. And this time we're going to talk about more than just our extrema. So let's start with our domain. So it's starting right here at -5. So I'm going to have a bracket -5. And then it goes to my asymptote right here. So I'm going to have a -2 parentheses, could put a little union and pick right back up at that -2. And then it stops right here at 2 with an open point as well, up here and down here. So it's going to go 2, union, 2. And then it ends right here at 4 with an open point. So I'm going to close with a parentheses. All right, the limit as x approaches 2 from the positive direction. So 2 is right here. And when I'm coming from the positive direction, that's this line segment right here. So it is approaching -2. Then if we're looking at the limit as x approaches -2, when it comes from the left, it's going down. And when it comes from the right, it's going up. So this one is going to be a does not exist because the two sides don't match up. And the limit as x approaches 0, while coming from the left and the right, it's approaching that 1. All right, I'm going to clear some of my drawings off the graph. Our next one says f of 3. So at 3, our f value right here, it looks like it's -1.5, -1.5. And f prime of 3, remember, is the slope of this line. So from this point to this point, I go up 1 and then over 2. So it's going to be 1/2. And our average rate of change from -5 to -3, well, that's going to be, let's say, f of -3 minus f of -5 over -3 minus a -5 means +5. So at -3, let's say that's 0.5 minus, well, at -5 it's up there at 1. And a -3 plus 5 is 2. So 0.5 minus 1 is a -0.5 divided by 2, which is going to give me a 1/4. If I take a half and divide it in half, that's going to give me a 1/4. So my average rate of change over that interval is negative 1/4. And now let's look at some of our extrema. So if I'm trying to find an absolute maximum, well, I've got an arrow up here. That means this graph is going to keep going all the way up. So there is none. There is no absolute max. And the same thing for my absolute minimum. There's an arrow going down right here, meaning it's going to go down forever. So there is no absolute minimum either. So let's see if there's a local max or min. So if I'm looking at my local max, if I look at this interval before the asymptote, there's not really a maximum. And then in this interval, there's not really one either. So for local max, I'm also going to say none. So let's look at local min. In this one, we've got that arrow, so it's not really a minimum there. But in this interval, I've got a local minimum right here. So I'm going to say that I have a local minimum on the interval, and let's just do this little segment. So from -2 to 2, I have a local min at x is equal to 1.5. And then the last thing that we're going to look at is where is our graph increasing and where is our graph decreasing. So our graph is decreasing from -5 to our -2 right there. So I'm going to put that down here, -5 to -2. Then I pick back up at -2 and it's decreasing until I get to that 1.5. So I'm going to do a union -2 to 1.5. And then at 1.5, it increases until we get to 2. So I'm going to come up here to where it says increasing, and I'm going to do 1.5 to 2. And this line segment is also increasing, so I'm going to do a union 2 to the end of my graph, 4. All right, so that was example 4. Let's look at our next problem. So the next one that we are looking at is going to deal with finding our extreme values, our extrema, when we don't have a graph, when we have equations. So we do have our extreme value theorem, which says if f is continuous on a closed interval a to b, then f has both a maximum and a minimum value on the interval. So on that closed interval, there's going to be some number that's a max and some number that is the minimum value. So kind of a translation, if f is continuous on the closed interval, that means that our x values are connected for all of the x values. And from x equals a to x equals b. So that's kind of that translation. Another one is that you could draw the whole, let's say, segment of the graph, which I can't spell, segment of the graph, without picking up your pencil. And another clarification is that this maximum and this minimum, since we're talking about an interval, that's going to be a local max and min for that interval. Okay, so let's talk about how to find our critical points, and then we're going to talk about how we can find whether or not those critical points are the maximum and the minimum. So, step 1 is take the derivative. So let's do step 1 over here. I'm going to do f prime of x is equal to, that 3 comes down times the 1/3, so it's going to cancel out, and I'm going to have x squared minus 9, and then the derivative of 24 is just 0. So there's my derivative. The second step is to set the derivative equal to 0. So x squared minus 9 is equal to 0. And this is where you're going to need to identify if there are any restrictions, so where the function is undefined from the original. And then if you do have a fraction for your derivative, you need to set the numerator and the denominator equal to 0 separately, because the numerator and the denominator are both going to give you critical points, because remember, it's whenever the slope equals 0 or when it's undefined. So the slope would equal 0 if the numerator equals 0, and it would be undefined when the denominator equals 0. So you do have to set them both equal to 0 separately. That doesn't apply for this problem. So we can go ahead and look at step 3, which is solve for x. So I'm going to add 9 to both sides. So x squared is equal to 9. And then I'm going to take the square root of both sides. So that means that x is equal to plus or minus 3. And those are my critical points for the function. So let's look at another one. This time I have f of x is equal to the natural log of x squared. So take the derivative, and I'm going to have to do a chain rule. I've got an outside part and an inside part. So for the outside part, the 2 is going to come down in front. So I'm going to have 2 times the natural log of x, and it's now going to be to the first power. And then I'm going to take the derivative of the inside part, which is the natural log of x, so it's just 1 over x. So I'm looking at f prime of x is equal to 2 natural log of x all over x. So now what I'm going to do is I'm going to, if we come and look back at the step right here, we're going to set the derivative equal to 0. And we need to identify if there are any restrictions where the function is undefined. So remember, we can't take the natural log of a negative number, so we're only looking at positive numbers here. So if we do get an x that's negative, that's not going to be a critical value. And I'm going to take the 2 natural log of x and set it equal to 0. And I'm going to take x and set it equal to 0. So x equals 0, that right there is just going to be a critical value, and we can take the natural log of 0. The natural log of 0, anything log of 0, you guys should remember, is, well, actually we can't do that. Sorry, I was thinking about 1. The natural log of 1 is always just 0. Sorry, if x is equal to 0, we can't take the natural log of 0. So this is where our graph or our function is undefined. And this one, let's go ahead and solve it for 0. So I'm going to divide both sides by 2. So I have the natural log of x is equal to 0. And like I was just saying, anytime you take the natural log or any log of 1, it's going to equal 0. So that means that x equals 1. So I was just getting ahead of myself on that last one. So our critical value is just going to be that x is equal 1. Our graph is undefined at 0, so that's not going to count as a critical value. All right, let's look at 3. I'm going to rewrite this function into something that's a little bit friendlier to take the derivative with. So I'm going to rewrite it as 4 minus x squared to the negative 1/2. 1/2 because we're talking about a square root, and negative because it's the denominator. So when I take my derivative, f prime of x is going to equal, well, that negative 1/2 is going to come down in front, so negative 1/2 times 4 minus x squared. And if I do negative 1/2 minus 1, that's going to give me negative 3/2. So my new exponent is negative 3/2. And I need to multiply it by the derivative of the inside. We do have a chain rule here. So if I have 4 minus x squared, the 4 goes away, squared comes down, so it's going to be a negative 2x. So cleaning this up a little bit, that negative 1/2 and negative 2 do cancel out. So my derivative, f prime of x, is going to equal x over 4 minus x squared to the 3/2. So our original function was a fraction, which means that we do have some points where our graph is going to be undefined, because we've got that square root in the denominator right there. So if I take that part, and I'll do it in purple up here, the square root of 4 minus x squared is equal to 0. So 4 minus x squared equals 0. 4 is equal to x squared, and x is equal to plus or minus 2. That's going to be where our graph is undefined. So if we get those numbers for our critical values, we know that those aren't going to be our critical values. So now I'm going to come down here, I'm going to take the top and set it equal to 0, and I'm going to take the bottom, that's a 3/2, and set it equal to 0. So x equals 0 right there, that's a critical value. Over here, that exponent, 0 to any exponent is still 0, so I'm going to have 4 minus x squared is equal to 0. So 4 equals x squared, and x equals plus or minus 2. So that would be a critical value, but that's where our graph is undefined. So those aren't going to be critical values. Our only critical value here is x equals 0. Okay, so now let's take those critical values and talk about how we can figure out where the maximum and minimum is. So I'm going to find the critical points just like I did before. So I'm going to take my derivative, f prime of x is equal to 3x squared minus 6x. I'm going to set it equal to 0, so 3x squared minus 6x equals 0. I can factor out a 3x, and I'm left with x minus 2 is equal to 0. So 3x equals 0, and x minus 2 equals 0. So x equals 0, and x equals 2. So those are my critical points. So now what I'm going to do is I'm going to make a table and include the endpoints of the interval and the critical points. So my table, I'm going to do it down here. I'm going to have my x and my f of x. So I'm going to take my endpoint of -1, then 0, then 2, and then my other endpoint of 4. Scroll down a little bit. So what I'm going to do here is I'm going to plug the x values into the original function to identify the absolute extrema. So my original function is my x cubed minus 3x squared plus 1. So I'm going to be plugging these numbers into that. So I have a -1 cubed minus 3 times -1 squared plus 1. So a -1 minus 3 plus 1. Well, those cancel out, so it's just a -3. Then when I plug in 0, I have 0 cubed minus 3 times 0 squared plus 1, which is just going to give me 1 because those go away. Then I have 2 cubed minus 3 times 2 squared plus 1, so an 8. 2 squared is 4 times 3 means I have a -12 plus 1. So that's going to give me a -3 as well. And plugging in 4, 4 cubed minus 3 times 4 squared plus 1. 4 cubed is 64. 4 squared is 16 times a -3 is 48. So -48 plus 1. So 64 minus 48 plus 1 is going to give me, doing some mental math here, gives me 17. So the lowest number over here is this -3, and the highest number is 17. So what I'm going to do is I'm going to say that the minimum of -3 happens at x is equal to -1 and 2. And my maximum of 17 happens at x is equal to 4. So there we go. Oh, and it does say right here absolute, so you could put the ABS in front for absolute. All right. Let's look at some more graphs here. It says find the extreme values and critical points where they occur. So if I'm looking at this first graph, we're not going to look at our endpoints, but I do have this point right here, and I'm going to say that that is my absolute maximum of 1, 2, 3, 4, 5 at x equals 0. And I don't have any minimums, so that's it. And let's look at our next graph over here. I'll do this one in green. Not looking at our endpoints, I do have this point right here, which is also an absolute max. This time it's of -1, and it happens at x is equal to -2. And then I also have a critical point right here because there's a sharp turn. So I'm just going to say critical point at x is equal to -1. Okay, our last one, and I'll do this one in purple. It looks like I've got an absolute maximum right there. So absolute maximum value of 3 at x is equal to -1. We don't look at our endpoints, but I do have an absolute minimum right here of -3 at x is equal to 1. And then I do have some critical points that are happening. So the critical points that I'm going to look at are right here at -2. That's not a min or a max, but I do have a 0 slope right there. And then I do have a sharp turn here, so that's also a critical point. We've already identified it as an absolute min or max though, so we don't have to identify it again, because remember our maximums and our minimums are critical points. So I'm going to say a critical point at x is equal to -2. All right, we do have one more problem that is a review problem from our last unit. So it says, let x of t equal t to the 2/3 give the distance of a moving particle from its starting point as a function of time, t. For what values of t is the instantaneous velocity of the particle equal to its average velocity over this interval? So remember, instantaneous velocity is when I take my derivative. So my v of t is going to equal, I'm going to bring down my 2/3 t. And 2/3 minus 1 is a -1/3. So it's going to be to the -1/3 power. So v of t is equal to, I'm going to do it as 2/3 cubed root of t. And I want to know where it's equal to the average velocity on this interval. So remember, average velocity means I'm going to do x of 8 minus x of 0 over 8 minus 0. So x of 8 means I'm looking at 8 to the 2/3 minus 0 to the 2/3 all over 8. So that just goes away. So 8 to the 2/3, well, the cubed root of 8 is 2, and then squaring it gives me 4. So I'm looking at 4 over 8, which is just equal to 1/2. So what I want to know here is, when is my 2/3 cubed root of t equal to that 1/2? I've got two fractions here, so I'm going to cross multiply. So 4 is equal to 3 cubed root of t. I can divide both sides by 3. So I have 4/3 is equal to the cubed root of t. And I can cube both sides to get rid of that cubed root. So 4 cubed is 64, and 3 cubed is 27. So I'm looking at 64 over 27, which is C. All right, that is it for this video. You do have a Go formative that goes along with this for homework, so please make sure that you do that. And remember, if you have any questions, you can always come to my tutoring times or ask me at the beginning of our next class period, or just shoot me an email and I will respond as soon as I see it. So make sure you do this Go formative, and you guys have a good day.